Yeah, so obviously thanks to everyone for joining this evening. I'm sure you've all had a pretty busy day. I certainly know I have. So yeah, I'll give you a brief introduction to myself, and then I'll sort of just hand over to the specialist, over to Martin. So yeah, my name is Graeme. I'm obviously hosting this new edition of Golang Live today. So obviously, like I say, thank you very much for joining. Today, I'm joined by my friend, Martin. He's a senior Go engineer over at Staking Rewards. The way I met Martin, I actually specialize in recruiting for Go engineers all across Berlin, Germany, kind of wider Europe. Obviously, stumbled across Martin, pure specialist, consider him my friend nowadays. And yeah, he's going to give this this wonderful presentation, all to do with the type systems comparing Go, C++, and Rust. So obviously, without further ado, I'm sure he didn't come here to listen to me drone on. So I'll let Martin sort of take the floor. Go ahead, Martin.
Thank you very much. So first of all, I'd like to say it's a pleasure to be here giving this presentation. And I want to thank Amicus and yourself for organizing this and getting it all ready. So I'm Martin. I am from the south of Brazil. Right now I'm residing in Europe with my wife, and I'm a senior software engineer. I have been programming in various languages across the years. I've been programming for over a decade. So I really like Go as a language. I also really like some other languages like C++. I'm going to talk a bit more about that, and Lisp. And I think now everyone is kind of peeking into Rust, so I thought that would be an interesting language as well for us to analyze here together. Also in contrast with Go and C++, because they kind of share the same problem space. So yeah, without further ado, let's just get into it. There we go. Go on to the slide. So the state of Go's type system. Let's get right into it. So we're going to have an index here. I'm going to talk a bit about what is a type system in a programming language. How does it impact software quality? And there have been objective studies around type systems and software quality. So there is a correlation between having a type system and how it works in regards to software quality and bug count and that kind of thing. We're going to contrast briefly static typing and dynamic typing. There are various ways to categorize typing systems, but static typing and dynamic typing are kind of the main pillars. And then we start getting into other features like type inferred languages, runtime type checking. But those are the kind of central pillars around typing systems. And then we have some, well, not some, a lot of more characteristics around that, but those pretty big separation there between those two. Then about features, we're going to check runtime type checking, which is something that is available in these three languages. We're going to see how it's done, or one way to do it. Then generics. Generics were introduced in Go 1.18, so not that long ago, and they really improved the language a lot. Took a long time to add them, but now we have it. Type constraints, they plug directly into the generics subject, so they are right after coming right after that. And then we're going to look into compile time duck typing, which is, I call it that, and you can find references for that name on the internet, but it's a quite interesting thing that some compilers implement. And then the last topic will be type erasures and monomorphization. Yeah, that last one is quite hard to spell, that one. Let's go. So what is a type system? A type system is basically a set of rules that is implemented either by a language specification, right? So your type system could be in a formal language specification. So for example, some very formal languages like Common Lisp has a specification. The type system is specified in that specification, and then it's implemented by various compilers. So it's built into the central definition of the language, and then it's implemented by compilers and interpreters. So, and it's a system of rules to determine what kind of values a certain variable can hold, and what operations can be performed upon those values. So if we have two numbers, for example, we can sum them together. If we have a string, maybe we can call a method on that string to turn that string into an uppercase string, for example. That would be part of the type definition for that string. And if we have a variable of type, string, then we can only hold strings. We can't hold an integer, for example, in a statically typed language. So that is actually kind of the niche problem that type systems solve. And then they also solve the question of relationships between types, because in many languages we can have subtypes. Then there is a relationship between subtypes and parent types that is formed, and that is also analyzed in either compile time or runtime, or a combination of both, where we say this type is a child of that type, therefore it works for the same set of operations. Okay. So an example here, we have, Python, we can, for example, just sum two numbers together and get a result. But then if we try to call a method that is not implemented by a given object, we get an attribute error. This error happens in runtime. It doesn't happen, there is no such thing as compile time in Python. Compile time analysis and type checking in Python. Built into the language. There are some type systems for Python that try to add static typing into the language, but it's not a core feature of the language. So if we try to call a method that doesn't exist in runtime while the program is running, it's going to give us an exception. That's just one example. So going back here, in Python, while the concept of types exists in runtime, so Python knows these two are numbers in runtime, it will not do anything ahead of time to try to prevent you from calling a method that doesn't exist, for example. It will become a runtime error. So how does a type system impact software quality? So some studies have shown that, you can detect errors ahead of time. So the things that I just showed is a good example of that. Some languages would not allow you to try and call a method that doesn't exist on a type. Various languages would do that. Most static type languages would do that. So that is one way. So a whole subset of errors is preemptively tried to be avoided right there. You can have improved reliability, right? Because you have this strict analysis phase ahead of the execution time. Things have to comply. Most of the time, they have to comply ahead of execution time. You can still get runtime errors, but they will be much rarer. Well, one example that we could say that we could still have a runtime error is what if the compiler is actually producing code that is still invalid. Your type system did its check, but the code that the compiler produced still doesn't quite work. So that's a way where we could, there is an error in your type system, and in runtime that's still going to show. But in general, if you are writing type safe code, you're not going to have as many bugs, although that comes with a cost. And that is where dynamic typing is good, where you can just work with your data and you don't have to worry too much about types ahead of time. So it's better for introspective kind of development and interactive development. Maybe dynamically typed languages are better, but overall, when we want extreme reliability, we tend to go into a static typed language. So yeah, we can have better documentation and easier refactoring. So if we have, I imagine lots of people here watching today have experience with statically typed languages, and you know how you can just hover over a symbol and it will show you what type that symbol is, because you can know that ahead of execution time. And if you want to refactor things, it's just easy to do that when you have your static types defined, because it plugs into the information that the refactoring tool can then use and leverage, because there is more information. You can just leverage that type information to do your refactorings. Yeah, so those are some points there. Yeah, and so comparing statically typed languages and dynamically typed languages, a static type is a language, statically typed language is one where the variables, the symbols, are bound to a specific type, right? And then once they are bound to that type, they cannot change anymore, right? So it's like if you say this variable A is an integer, you cannot later on reassign A to be, change its type to be something else inside that scope where that A was defined. This generally applies to essentially everything in the language, like global variables, local variables, function parameters, return types, exceptions, and all that. They are all typed in a statically typed language. And yeah, and so wherever there is a value, even if it just typing the value 10, for example, the compiler will infer that for you, and it will have internally, it will know this type is an integer or some other number type. And then the language has this phase where it tries to apply compatibility guarantees. You know, are you calling the correct methods? Are the operators you're invoking on these types, are they valid for those types? And there is a whole analysis phase there ahead of execution time, where the compiler will try to guarantee that everything is matching, everything is working correctly, at least when it comes to type compatibility. So that's where part of that reliability we were talking about earlier comes from. Yeah, and some languages will actually retain type information in runtime. So you can actually write code yourself to do, you know, I want to ensure that this is actually this type, because in runtime the type information is available. So let me just show a quick example here in Go. Go is statically typed, and we have two functions here, one in Go, one in Rust. We're just trying to say if a number is even. So we just say a module 2 equals 0. That will give us 0 if the result of that operation will be 0 if a is an even number, and that expression will be a Boolean value, true or false. The same thing here in Rust. So we see here that we have the type for the input, for the output, and the result of that expression needs to match that the type of the function is returning. Same thing in Rust. Okay. And a dynamically typed language is one where the variables are not bound to a specific type. So A could be anything at any point in time. It could change, the variable A could change its type in runtime in the same scope. Dynamically typed languages, every single one of them I have come across, they retain type information in runtime. So the Python interpreter knows your numbers are numbers when it's executing them. When it's executing operations on them, it knows the types. It just doesn't apply any ahead of time analysis of type compatibility. So even if we add something like MyPy on top of it, which is a static typing system for Python, because Python is so dynamic, where you can even create new types in runtime, it can't catch every possible scenario. The language is more expressive than an ad hoc static type system can guarantee safety for, right? So MyPy and those other tools, they're great, but they're not the same as having a language where you cannot write a type unsafe code, like say Rust, for example, or even Go, for example. Well, Go does allow for that. We're going to get into that later on. Yeah, and then nothing has to declare any return types. They will just return whatever they want to return. Internally, these interpreters for dynamically typed languages, they have a single type, like object, which is the most generic type. And then every single thing in the language is a subtype of that type. And it will just unify everything inside this type. So actually, if we look at the tree, at the abstract syntax tree for Python code, the most generic way of that working is just a tree data structure of Python objects. And then in runtime, it's going to figure out what that object actually is. So operation compatibility is not guaranteed ahead of execution. Yeah, and that's it. So everything will essentially become a runtime error. If you make a type mistake, a type related mistake, it's going to become a runtime exception, which is the example I showed originally. Perfect.
Sorry to just jump in there, Martin. Yeah. I've got a quick question from there, from Louis. He says he noticed the uppercase versus lowercase typing of the even function in the example. He's wondering, how is the concept of private versus public functions expressed in Rust?
I'm not entirely sure exactly, to be honest. I imagine you have a keyword. In Go, yeah, in Go we have upper, so for people who are not really familiar with Go, an uppercase letter here, and as the first character of the symbol for this function, means this is public. In Go, I would imagine you have a word like pub for denoting your how you can access that, but I'm not entirely sure. Sorry about that.
Perfect. Well, cheers for your question, Louis. One thing I did forget to mention at the start of the presentation. A few people have sort of asked kind of midway through. All the slides, by the way, will be available in the recording on our YouTube channel. So feel like if you want to kind of revisit anything, feel free to sort of visit over there. You should also be sent everything sort of to your email also. But yeah, feel free to kind of get involved. By the way, it's meant to be as interactive as possible. So any questions or anything you kind of want to query, yeah, feel free to sort of just ping it in the Q&A down below.
Absolutely. Thank you very much for your question. So yeah, yeah, feel free to ask questions at any point in time. So here we have the same example in even function in Python. Does the same thing, but we don't have to declare any types. And well, we can. Here we have another example of having a runtime error where we're trying to apply the module operator on a string, and it doesn't work, right? So okay, so now we're going to get into those features I mentioned earlier, and we're going to compare Rust, C++, and Go in this regard. So we're going to go into specific features, how the languages deal with them, and how they work internally. Okay, now Go, we can do runtime type checking. Runtime type checking is when we are in runtime, so our code is trying to do something in relationship to the type of a given variable. So the concept here is that in runtime, the language still retains that type information. Sorry, whoops, hold on, what did I do? There we go. So we can. Is my screen still being shared?
Yeah, I can see that.
Okay.
There's a little grey box at the top, but I can see your screen nonetheless.
Okay, wonderful. Okay, so in runtime, we still have that type information, right? So for example, here we have an empty interface in Go, which can literally be any value. It could be anything. It could be a struct. It could be any kind of built-in data type. And we are just saying this value is the value 42, and then we have our block of code here where we're trying to cast that. We're trying to say, is that a string? And then we say that value is a string. Is it an integer or is it an unknown type? That is not the last branch of execution there. So in this case, it would print the value is an integer because that is an integer. But there is no ahead of time analysis. Well, the compiler can't know ahead of time what that thing is because I didn't declare that to be an integer. I declared it as it's an interface, an empty interface. It's whatever. We'll deal with it later on. For a long time, this is what everyone was forced to do in Go before the introduction of generics. We had to try to convert things into things or call methods into things, and if it failed, we had to deal with the errors ourselves. The compiler didn't have any kind of understanding of many things because we didn't have generics. So we had to resort to runtime type checking and runtime method dispatch to do everything. In Rust, we can do a similar thing. There is a trait that we can use called any. And with the trait any, we can inspect that we can use pattern matching, and we can inspect that value is a given type, right? So we could do the same thing. We're going to match on value, and then we have these cases here. And if any one of these is true, it's going to dispatch that handler at the on the right hand side there. So here we say the value is 42. Same example as the Go one to be easier. And then we say, well, if that value is an integer of 32 bits, we print the value as an integer, so on and so forth. In this case, it's going to match that one, but we are doing this again in runtime, right? So in this case, we are using the any trait and that any trait will retain type information. Go strictly doesn't have to retain type information. It's just that we are using that trait, so it will have to retain that type information in this case, and then we can just compare it in runtime to determine, what type of that variable is. And then C++, very similar concept. We have a standard any, kind of very similar to Rust. Maybe Rust adopted the idea, or C++ 20. Seeing as it's a new standard, and we have the same thing. We can point standard any to any kind of value, and it will retain type information, right? So the runtime type checking here is being done in these languages by these special types, right? Any and any in C++ and Rust. In Go is part of the language, so the language will not ignore your types. You can still have access to all of them in runtime. C++ and Rust, you have to retain that explicitly, because they will try to remove as many types as they possibly can in later optimization phases of the compiler. So, for example, if we were just creating a function in C++ that sums two numbers together, if we were to look at the assembly code, there would be no type definition in that assembly for a number. It would just try to use the CPU registers to do that, and native byte boundaries to determine what the operations are inside the instruction set of the machine. So we have to ask the language to retain that type information using those specific types or a variation thereof. Now generics in Go, they were introduced, as I mentioned earlier, in Go 1.18, and we were missing this feature for years and years and years, but they finally arrived. And what they allow us to do is they allow us to define generic functions, generic methods, and generic structs. So in this case, I have a generic function called max. Max takes a type T, which complies in this case to the type constraint comparable. So comparable here is a type constraint. And then I say, okay, I have this type T, must comply to that constraint. And I say my arguments now are a slice of that type T, and I will return one of those T to you. And what the code will do is it will iterate on that slice of items and just find the one that is the largest one, the biggest one of them, and return that one. But we see here that we aren't using this comparison operator, and that we can guarantee that that operator has been implemented for the objects inside items, because they all must comply to the comparable type constraint. Right. I'm going to go into type constraints later on as well. It's quite a complex subject, but here we see generics and type constraints in a single slide. So the actual usage in Go would be, say I have a slice of integer, a slice of float, a slice of strings. I can just call max on them, and it will call that function for each one of those specific types. Well, actually, it will specialize these functions. So actually, in the code, there will be, you don't see the code, but it will generate the code for you. For each one of the usages of max, it will create one version of max. So there will be a max for floats, a max for integers, and a max for strings.
Okay, cool. Sorry to interrupt again, Martin. Apologies. Just got a quick question. Another one. So they've mentioned they thought that comparable only implemented equality and inequality, not greater than, less than, etc. Yes, so I'm not sure if you can shed any light on that.
I think comparable does implement these comparisons of operators, but we could double check that later on. But because I tested this code, so I'm pretty sure it does, but maybe I'm wrong. We'll have to double check that later on.
Okay, cool. Cheers for clarifying. Thanks for the question as well, by the way.
Yeah, absolutely. Okay, so we have these usage examples, And now in Rust and these other languages, we have the same kind of concept. I have also an array of type T here, a reference to an array of type T that holds T, and we're returning a single T. And here we have what would be our type constraint. This is actually a trait in Rust, so I can say T must implement this trait. And then with that, I can do the comparison as well on each one of my numbers. Well, not necessarily my numbers, but whatever implements this trait. And then we can compare them and return the maximum. So very kind of similar to Go, except that we are not using a Go type constraint naturally, because this is another language. We're using a trait, but it's kind of the same idea, really. And like Go, it will also create various instances of max, various functions, and it will specialize in compilation time. So there is no runtime overhead for any of this in either Go or Rust. It's all done in compile time, and then it's further type checked later on as well. Here is the example in in Rust. We're using the vector macro to just create vectors with these types, and then we can just call max, and we'll have the max float, the max integer, and the max string. And C++20, same thing. We can now we have templates in C++, where we say we have a template. It takes a type named T, which is the name of a type, and it must satisfy that interface as well. So we can say requires this interface, and it must implement that interface. And then we can just implement max, essentially the same idea. Very similar to both. It will also specialize the functions, so very similar. The same one-to-one translation between languages there.
Okay, perfect. Then, apologies, just to kind of rewind slightly. Yeah, got a couple of questions kind of fly in there. I figured I'd kind of wait until you kind of got your point through. So a question from Carlos this time. What's the performance difference between using one typed function versus having different dedicated functions? And he's gave a few examples like max int 64, etc., max float, etc.
What would be the performance difference between writing ourselves the max function versus using generics?
Yeah, so I'll just repeat the question. Obviously, probably appreciate I'm not the most technical person.
No.
So the question phrased as, what's the performance difference between using one typed function versus having different dedicated functions?
There is no performance difference. So what the compiler will do is it will take your templated kind of functions, right? Your functions using generics, and in Go, in Rust, and in C++, there is no difference, because it will create these as if you had written them. It will specialize those functions for us based on how they are used. So, for example, when I use max with a vector of integer, it will create one version of max for integers, and it will compile that into its own native set of instructions. So it will know if I'm calling max with a set of integers, I can jump to that specific function. And because it's using multiple passes there are multiple phases inside the compiler, it can optimize each one of those functions individually, right? So it's like it could expand max into an int 32 specialized function, for example, and then another phase of the compiler could take that and inline that function. If it's only ever called inside a given another given function, it could inline that if it sees that would be a good optimization. So it will do what you would do if you had expanded the code yourself into the specific types. It will do that for you. So there is no runtime performance penalty.
Okay, perfect. I trust that kind of answers the question. Got another question here. Okay, perfect. Before we move on to the next question, Carlos said, awesome, thanks. So I answered the question. Okay, cool. And now Mohammed is wondering, do we need to specify the type of max function before calling it?
No. No, actually we don't. Well, maybe some languages would, but these languages don't. So for example, here we see the Max example in Rust. What it will do is it realizes that the type of nums in this example, for example, is a vector of integer, right? So it realizes, oh, you gave me a vector of integer, of int 32, for example. And what it will understand is that if the type of nums is a reference to a vector of type t, then t, in that case, must be int 32. It will do type inference, and it will infer the type based on the usage. So how you call Max, it might be able to determine, it will very likely be able to determine, oh, you are, because all these types must be known at compile time. It will say you're calling Max in this case with a vector of integer, in this case with a vector of float, in this case with a vector of string. And based on the usages, it will create one version of Max for each one of those usages with that type. But if you were to repeat that, say you call Max 30 times using a vector of integers, it will only naturally generate one function, not 30, but it will be one function per type. So it will expand those for you automatically. But you don't need to say max of int 32 and then pass the vector, because it will infer the type based on the usage in compile time. So again, no runtime penalty.
Okay, excellent, perfect. Thank you for thank you for answering that question, Martin. And thanks again for the for getting involved. Okay, cool. Thanks again. I'll let you continue.
Absolutely. If there are more questions, just keep them coming. Thank you very much. Okay, so generics. Now we're going into a very, very nice subject here, where we're going to talk about type constraints, right? So I mentioned earlier that in Rust, they were using traits there, and in C++ they were using interfaces that those template parameters had to implement. In Rust, in Go, we have something along those lines, right? We have something similar. So, for example, let's imagine that I have a function called sum, and it takes a t of type any, type constraint any, right? This is where the type constraint comes. Any in Go is an alias for an empty interface. So I could have written an empty interface or the keyword any. They are the same thing. But any is now kind of gaining traction. People are not using empty interfaces as much, but they are the same thing. They are semantically the same thing. Now, let's say I have two parameters, A of type T, B of type T, and I return T. And I'm just trying to sum them. I'm just trying to say sum those two together. But they could be anything, right? The compiler will actually produce a type error for us in compile time, right? Which is good, because we want to have the error in compile time, not in runtime, because in runtime we would have to handle it, or our program could crash or something like that. So we want to catch as many errors ahead of time. And this would be also the difference between, saying I have a T of type that is any, type constraint any, versus saying A any, B any, and returns any, because that would generate a runtime error. In this case, now we have an alternative that is verified in compile time, which is good. So a compile error, in this case, it will show, the operator plus is not defined, because I cannot guarantee that that operator has been implemented for A and B when there could be anything. There is no, it can't guarantee that. So it doesn't even try to guess anything. Unlike the some other examples we were seeing earlier, it doesn't even say, well, maybe for that occurrence, that is an integer, integers do implement plus, so maybe I could infer something and that would work. No, it takes a very orthogonal approach and just says you have to explicitly define your type constraints, and that doesn't fly because I can't guarantee anything ahead of time. And I would not infer. So the compiler is very kind of restrictive in that way. And well, we could argue about that. But so now if I change that any to a different type constraint and I say, look, that is an integer. Now it has all the information it needs ahead of time to guarantee type safety, and it will say, okay, fine, that will print 11. It will sum those two values, and that's it, right? Again, it will specialize sum for int, right? So it will create one version of sum specifically for int. We could also use type unions. So, for example, I can take two primitive types. I can say this t is either an int or an int32 for that single type t, and I have a and b of type t and returns t. And here in this example, what this would print, you can see I have some print statements here. They would print the type of a and b. Now, because I converted b into an int32, and I said that the type constraints, that there is only one type in this function, which is t, they will both be int32. If I were to run this code on standard output, I would see int32, int32. So a and b are the same type. Because b is an int32, it will infer that a also must be an int32. And because it can do a type conversion for us, it will do a type conversion for us. But it will, if I were to remove this function call here and just pass a 10, they would both be int in that case. So there are some details there which are quite, well, they're quite in the trenches of the language, but just thought I would bring it out explicitly in this example. So I can combine these type constraints to create further type constraints. So, for example, here, if I create another type constraint, I'm saying this could be either a float, 32, 64, or integer, two types of integer, and I try to compile this code, it doesn't quite work because it can't convert implicitly the 10 to a float, right? And it says at 1.2 that's a float. Now both variables there, a and b, they must be float 64 in this case, which is what the compiler understands our value as being. And now, unless, you know, if I were to convert that explicitly, that would work. But because I passed an int, it will not do any kind of conversion for me in this case. And it will just say, look, I can't have this, violates the constraint that you applied here, where you're going to have a single type being any one of those things, but it will have to be a single type, and those two variables must comply to that type, that single type. So they can't have different types in this case. Do we have any more questions? I'm not sure.
Not quite yet. Nothing's kind of came in the last moment.
Okay.
Actually, now you've said that, bear with me.
Okay.
Here we go. Yes, so actually, as you asked that just now, one's kind of flown in. So Mohammed is asking, can it be dangerous to call sum 100 int 8 brackets 3? I assume there is no way to go to detect this, right? Forgo to detect this.
An int 8?
If you need me to repeat the question, yeah, for sure. Yeah, so can it be dangerous to call sum 1000 int 8 3? I assume there is no way for Go to detect this, right?
I'm not entirely sure if that goes, that's an integer overflow, right? You're trying to take the value 1000, which is going to overflow the integer. I'm not sure if Go will detect integer overflow in compile time, or if you're going to have to try and deal with that in runtime. I'm not entirely sure. Some languages do that, right? So Rust, for example, will do that. Rust will help you avoid overflow errors. It's built into the type system, and it's checked in compile time. I'm not sure how Go handles that. It would be smart if they were following the same approach. I'm not sure if it will. I think it will overflow. I think it will overflow, but I'm not entirely sure about that particular. But in this case, you know, in this case, if you were to call sum with int 8, it's not going to be compatible. So this is maybe answering your question is, can I guarantee that I will not overflow because all the values I'm interested in can be represented in, you know, are being checked for inside this function. And then you could say this has to be, you know, it can't be a bigger value because that lower, I mean, your int 8 might overflow, but you can't pass an int 8 to the sum function because it's not one of the allowed types in the type constraint. Does that answer the question? You will have some protection, but not against the overflow, just about what sum accepts. If that answers the, I'm not sure if that answers the question.
Okay, cool. I'm assuming that will answer the question. But yeah, sure. Louis made a point as also regarding the comparable constraint question. Yeah, Mohammed said, understood, thanks. Perfect. Yeah, sorry, going back to Louis' question. Regarding the comparable constraint question, according to the spec, is a comparison one operator. The comparable constraint thus indeed includes order operations. The language is, as argued by the community, rather confusing when referring to ordered versus comparable operators. And he noted this choice of terminology probably is what confuses you. Yeah, I'm not sure what your thoughts are on that.
Yeah, absolutely. The language is confusing in various aspects, but I agree with that. Absolutely.
Okay, wonderful. Yeah, another question just flown in there from Justin. Can you call a function with multiple different generic types, or do all generic inputs, can there only be one type?
You could have multiple specifications. So you could have multiple type definitions here, type generic types. Yeah. And you could have them. So I could have T, you know, a type constraint, comma, I don't know, another letter like U, and then another type constraint, and I could just use them here as the part of the types that I can use as my types for the parameters and for the return value. So you could have multiple, and you can combine them in a way, right? So I could say I have T, which is float 32, float 64, comma, I have a U, which is a slice of T. So you could create a type, define a type constraint and a type parameter in relationship to another one that you just define, you know, just prior to your current definition. So you could combine them together. Okay,
perfect. Thanks for that as well. So Sergey's made a point. In case of int 8, the Go will catch the overflows.
Okay.
Yeah, perfect. Okay, cool.
Awesome.
Perfect. Okay, well, cheers for those questions, guys. I'll let you. I'll let you crack on, Martin.
Yeah, they were great questions. Thank you very much, everyone, for the questions, the insights, and the extra information that you're bringing from the internet. Thank you very much, and for your own knowledge. It's amazing. Okay, and so in this case, we're just moving on. If we provide the correct type, in this case, again, everything will become, in this case, a float 64, which will be compatible with the type constraint that we've defined here, and it will satisfy that and will return 11.2, which is the right result. Now, if we can also assign names to our type constraint. So in this case, I'm just replacing that with this. Oh, and adding int64 there to the set of that type constraint. But just to make it easier, because we don't want to repeat the whole set every time, right? We just want to assign a name to it and just do that as well. That works as well. Same results as before. These two will be float 64s, and it will work. Just check how we are on time. Yeah. We don't have that much long, but let's go on. Another kind of type constraint I could have is I want to create an interface here, which the internal type of that type that will implement this interface, the underlying type will have to be either a string or an integer, and it will have a single method greet, right? So this is a type constraint as well. And we're saying it needs to have that method, and its underlying type will have to be either a string or an integer. And that's what the tilde there denotes. It denotes the underlying type of this type that will implement this interface needs to be either a string or an integer in this case with this union here. So for example, I have a type called custom string, which is a string. So it's a type alias. And I'm just saying, well, but custom string is actually extends string because it implements greet, right? And I'm saying just, well, when we call greet, we're going to say hello, I am, and the string itself, right? And then we have a generic function here called greet, which takes a greeter, right? So it takes one of these, and we know the definition of greeter, and then we're just going to call greet on that greeter, right? So here everything, the types are all satisfied and everything will work. And then we say we have a custom string called John, and we're going to say greet on that string, right? On that custom string. And then what greet will do is it will call this, well, it will be specialized for that type, for the type greeter. And it will call the greet method from that interface. And that will then in turn call that, and it will print, hello, I am John, right? We could also have another implementation for the integer in this case. And we can then see the whole cycle of I'm creating my own type constraint. It has both a constraint in terms of the underlying data type for that, for whoever is going to use this constraint, and the methods as well. I could have return types here and parameters as well, and then each one of those implementations has to comply to that interface and need the underlying data type must be one of those. So I can plug into the built-in types there. And this will work, and it will all be checked in compile time. So this is quite expressive and quite unique to Go. So this is quite a unique approach. There is no, Rust and C++ will do this, the type constraints they do with interfaces as well, but they don't have this notion of binding to an underlying type, to a specific built-in type that can be extended and that I can get the direct data implementation. So in this regard, Go is quite unique. Yeah.
Okay, cool. Just jumping in there, Martin.
Yeah.
Quick question from De Beer this time. He's wondering, does this need to say type custom string implements greeter, because custom string already implements the underlying type?
I don't think we can use the keyword string, the built-in word, to just try and extend it. If I'm understanding the question correctly, do we need a custom string, or could we just use string? Is that what is meant?
I'm assuming so, to be fair. Although I'm sure DeBeer will kind of pop another question in the chat. Should that be incorrect? In the meantime, Raphael's kind of pointed out that Python has protocols which are basically the same thing as Go's interfaces.
Yes, Python has protocols which are the same thing as Go interfaces. The big difference would be that in Python it's all happening in runtime, and so you're calling a method on some object. The method dispatch is happening in runtime. There is no analysis phase ahead of time. In Go, you can determine the dispatch. So you can determine the function that you're actually going to call before execution. And in Python, it's all deferred to runtime. But it's very similar concept, yeah.
Okay, cool. Louis is getting involved once more. He's wondering, is set algebra supported by the constraint system?
Not fully. No, not fully. I tried using it. It's not fully supported. So it's not quite as expressive as algebraic data types in some other languages like Rust and Haskell and ML. And it's not fully there. It's a step ahead, right? It's an improvement, but no, we can't say I have these two types and I have a subset of that type that I want the compiler to kind of infer. You know, we can't really do those kinds of semantics right now in Go. I recall reading somewhere that they might introduce that at some point in the future, but they're also trying to keep the implementation simple. So I'm sure there is a balance there that the Go team is using to decide these things. And simplicity might be one of the, well, it's surely one of the criteria. So no, it's not as expressive as algebraic data types.
Okay, perfect. Thank you for, thanks again for the questions, and thank Martin for kind of taking the time to answer them. That's all the questions for now, by the way. So feel free to sort of proceed.
Absolutely. Thank you very much, everyone, for your questions. And it's a great insights. And then how would we do that? Oh yeah, this is now, okay. Type constraints, I didn't really go into C++ and Rust that much because they are handled differently in those languages, but they are using interfaces and traits in Rust. In Rust and C++ is using interfaces, as I showed earlier. Now in C++ has a really nice feature, which might not be that much, might not be very well known. But C++ has a nice feature where we can do compile time duck typing. Okay, what do I mean by this? I mean that you're going to figure out what method to dispatch in compile time. Okay, so for example, here I have a template which is taking two types, T and U, and I'm just saying, look, I have my sum function. Again, the same examples. I'm going to compare, I'm going to sum A and B. And notice that we have the operator plus there, right? So the operator plus, C++ understands that as one operator. And any type in C++, any struct, any class can override that operator. So we have operator overloading in C++. So my sum is a generic function, and it's going to return a T. But it could work with any two types, right? Well, not any two types, but many of them. So here we have an example. I am taking the integer 42 and the double the pipe, and I am summing them right together. So it will, again, it will take sum. It will realize, oh, I is an integer, D is a double. It will create a version of sum for those two types, and it will create another version of sum for those two types. So there will, internally, there will be two versions of sum, one for each one of those usages. They are distinct, right? So calling integer double is different than calling double integer. I also wanted to show that here. So this line will actually print 45 in the standard output. It will coerce the double to an integer and print 45. And the second version there, it will coerce that integer to the double and return a double, right? So it will keep that extra information there. Will return 45.14 there. So based on how you're specializing the function, you're going to get more numeric precision, which is fun. But we see here that C++ said, okay, I have a plus implementation of that operator for int and for double, so it will work, and it will determine that in compile time. Now, if I try and use standard strings, that also works, because strings will have, they also define a plus, so that works. And that plus operates on strings, so it will work. Now, if I were to using raw C strings, right, pointers to characters, that won't work, because that does not implement the operator plus. So here we have a compile time type check that says I can't do that, but it realized that you can't do that because you don't implement the plus operator for raw C strings, right? Raw pointers to characters, and it will do all of this in compile time. So when I say compile time duck typing, I mean being able to determine the method that you're calling in compile time and verifying whether those types implement those methods. In this case, it's just that, the plus in C++, the operator, you can actually overload it with a method. So it will do all of that for you. And it will determine this ahead of time. But notice how I didn't have to bring an interface into the function definition here. I didn't have to say T and U must implement that operator. And this is what I mean by this duck typing thing. It is very much like Python, where if you have your plus define your add, underscore add in Python, you can override that. That will hook into the plus operator. I didn't have to define an interface and say T and U must comply to that, to that operator. The compiler figured that out for me automatically. So that's very clever, and it's verifying all of this in compile time. So, and this is a very powerful concept that I have not seen many languages implementing to any kind of capacity. Now, it's very kind of maybe dark magic what's going on, right? We are inferring types, and we are specializing functions, and we are then trying to figure out if those types implement a method, and then we are ensuring that things are there is an implementation. So it's doing a lot in compile time, but it's a very nice feature, and we're not binding this to any kind of strict type constraint as we were earlier in all languages there. So I have a type constraint, but it's very implicit, and it's inferred by the compiler, which is very cool.
Perfect.
So C++,
quick question, just flying in from Louis, wondering what would Go do in this circumstance?
A great question. So Go in Go, we kind of have to use interfaces. It won't do anything basically. In C++, the compiler will do a lot for you, and it will figure out this type implements that, so I can call it with that occurrence of some. In Go, we will have to make that explicit using using an interface, and then we can specialize on that interface, and then naturally we can call things. But here, this code is explicitly very naive in the sense that I'm casting things here, and these could fail, right? These things could fail, but I just wanted to make that explicit. If we were to program with defensive programming here, checking whether our type conversions work or not, we could write safe code in this case, but we have to put in that little bit of extra work to have an interface and to have everything be compliant through the interface mechanism, where then I can start taking summables as types for inputs and outputs. But yeah, basically we don't get as much compiler help here as we get from C++. We have to be more explicit about things in Go. And use interfaces.
Perfect. Just a comment on that again from Louis. Mentioned that explicit is better than implicit. So I'm sure that's something,
that's a good point as well.
Cool. Okay. Well, cheers for taking the time to answer those questions again. Let you crack on.
Absolutely. Thank you very much for all the questions and for the conversation. And then the last topic that I wanted to touch on is type erasures and monomorphization, which is when the compiler will try to erase types as it either compiles code or before it starts running code, right? So Java will do some of this stuff where you have your generics. It will not really expand them into multiple versions. It will create one version for the type object in Java. And inside that method, it will do typecasts, and it will do the right thing so that it works with every single usage of that generic type that you specialize your type with. And monomorphization is the process that I mentioned earlier of, I have a generic function. Let me come back a little. I have a generic function. Let's come maybe here. Let me try and see. No, I have an example at the end. There we go. Okay. So Go will, for example, if I have a t any here, I can use this any. I'm not doing anything forbidden in this case. I'm just printing out some stuff. It will create one version of print value for hello, for 42, and for true, right? For the string, for int, and for the boolean, and it will create those three versions of functions individually. Right, and so this is the process of monomorphization. It is taking each one of these occurrences, figuring out the types, and creating specific functions based on those types, and then further compiling that as a second pass in the compiler. That process is monomorphization. So none of these languages really implement. Well, C++ and Rust do implement type erasures, where if we have, as I mentioned earlier, if we have just a function that sums two numbers and we use the most aggressive compiler flags, the actual types will be vanished. There will be no kind of runtime type information there. So type erasure is a concept present in both Rust and C++. In Go, there are no type erasures because we have all the information about the types available in runtime, right? So for example, here I can actually print the type of each one of these values, and this will happen in runtime. I still have that type information there, as I mentioned earlier. So yeah, that is the process of just specializing these functions for each specific type that we have. And these will all do the same thing, right? Okay, in this case, in the case of, sorry, go on.
Sorry, Martin, for jumping in there.
Yeah,
just a quick question kind of flow in. He's wondering, is this what in template meta programming at C++ is referred to as template instantiation?
Yes, exactly. Yeah.
Perfect. Apologies for interrupting you there. But yeah, cheers for answering the question nonetheless.
No worries. That's a good question. Yeah, it's the same concept. Exactly the same concept. But you're taking the C++ template and you're expanding it, and then you're doing your type checking on top of that, right? Because a template could expand to an invalid usage, but the type checker will catch that for you after the template has been expanded. So there are multiple, as I mentioned earlier, there are multiple phases there, but it will do the right thing. We'll expand the template and then do type checking based on that expansion for all the usages of that template. Yeah. In the case of Rust, we see here that we have to use again the standard any trait to retain the type information for that T there. So in this case, the code that Rust will produce will retain some type of information about T through this trait. And in Go, we didn't have to do anything. We could just say print the type of this variable, because Go will retain type information. Rust will try to remove all the type information, but we can ask for it to retain that with specific traits like standard any. Yeah, and the same thing essentially in C++ as well. So yeah, we can see we are using a specific function call here to retain type information in runtime. And that way the code will be, probably the output will be kind of similar to what Rust does, where we are asking it to keep the type information in runtime. Yeah, so we have to use these types for that. And I think that would be it for the presentation. Do you guys have any other questions? Any other topics?
Yeah, I was just going to say, Martin, by the way, thanks very much for giving me the green light to kind of interrupt you as you were speaking.
Yeah, absolutely.
I appreciate it can be a little bit disrailing sometimes. Thanks for allowing me to sort of interrupt you now and then. Quick question at the end here. Dimitri's wondering about the example with a greeter interface and a generic function. What are the benefits of using func greet t greeter brackets gt instead of just simple func greet brackets g greeter? I hope that makes sense.
You mean like just using the greeter as the type for G directly and not using generics? That's probably what is meant.
Waiting for a response. In the meanwhile, Louis just added there, what a fantastic presentation. He said that we are two proper Gs, so thank you very much for that, Louis. It was fantastic compliment. And Dimitri says yes, that's exactly what he was asking.
Yeah. So the idea here is, so thank you first, Lily. Thank you very much. Really glad that you enjoyed the presentation, and thank you for your comments during the presentation. Now, answering Dimitri's question, the difference is that I can guarantee that there will be that the type I'm specializing for needs to comply to the category of those built-in types, for example. So I can say, well, it could either be a string or it could be an integer, but it needs to be one of those two, right? This idea of a set, which is what was referred to earlier on as an algebraic data type, it starts going into that direction, where I'm saying, well, this is either one or the other, right? And this is something that is very common in languages like Haskell and ML, and Rust also adopted some of those ideas where I'm saying, well, it has to be one or the other. That concept wasn't really present in Go. We couldn't really express this has to be either a string or an integer, and it needs to have that Greek type there. But granted, interfaces are checked in compile time. So if you feel like you don't need any kind of extra flexibility, then you could just say, you know, I just want the interface there, and I don't need the generic. So there is a cross. You're right. There is a cross section between these two concepts, where interfaces will sometimes suffice. Sometimes you want to express a type in relationship to another type. So I could say, you know, I have T of type greeter, and I have a U of type it's a slice of greeter, and then you can also use those there. You can combine them, one in relationship to the other, and they could also themselves, in this case, specify constraints about the underlying type that is used by that type, the actual byte representation. So it's a bit more flexible because you can express a bit more going into the set theory around types. It's not quite as powerful as full algebraic data types yet, but it's a step in the right direction. And sometimes we will come across some things that you can't really quite express with an interface, and that will better be moved as a generic type. And sometimes it will not be needed, so you can just say, if that doesn't need, I can take a step back, just work with the interface, assign use the interface as a type there, as a type parameter, not as a type constraint. Yeah. I hope that answers the question.
Okay, perfect. Yeah, final couple of questions flying in now. Yeah, very quickly, Louise asked one more time. Do you see value in languages including type erasure in their spec? And second question, does Rust resemble JavaScript in any way?
Do I see the value in having type erasure in the spec? That's a great question. I think so. I think I do. Because, well, we can think about what Java does. Java will have, it will use type erasure, and it will change the instances of the generics for object. And then inside the code, it will specialize that code to deal with the types that it needs to deal with. As part of the specification for a language, I think one of the advantages having it just there would be just having it in the specification so that it's not up to compiler implementers, right? So if you have a definition of we're going to do type erasure or we're not going to do type erasure in the spec, it's probably better than leaving that to compiler or interpreter implementers, right? Because then they will have to make the decision. And now it's a very gray area in relationship to the standard. So I would say just having it there, you know, a decision, probably a good idea. Technically, I kind of like the approach that Rust and C++ go, where they try to apply as much type erasure as possible, because it will tend to give you just great performance. Because if you can erase a lot of the types, you're not really doing, you know, as much in runtime. I mean, if you don't need to check types in runtime, you you have already decided what to do with a particular type ahead of time, right? You dealt with that earlier. There will be no type specific runtime performance penalty there. So I think there is value to that, a lot of value to that, particularly when it comes to high performance computing. I think that would be my answer.
Okay, excellent. I think that's pretty much all the questions we have then. So just to kind of wrap up then, obviously, thank you very much for the presentation, Martin. One thing I'm going to chuck in there before we leave, Mohammed's mentioned here, obviously, thanks for the presentation. He said it was very much worth staying up until 3 a.m. in Japan for. Yes, there's obviously huge thanks coming from Mohammed there.
Thank you very
One
much.
thing I will mention, obviously, before we kind of wrap things up, obviously the recording of the presentation will be available on the Amicus Recruitment YouTube channel. So feel free to sort of jump over there if you kind of want to rewind or you missed anything. But yeah, that's pretty much it from me. Obviously, huge thanks again, Martin, for the great presentation. Thanks again for taking the time to do this. And yeah, if you have any final comments, yeah, I'll let you sort of conclude.
Yeah, I don't think I have any, well, you know, I think if I were to have any comments, I would just say for all of us as a community to get familiar with type systems and how our languages are actually implemented, not only in relationship to type systems, but in general, how that code is actually being executed at the bottom level and how all the transformations happen between what we write and what eventually becomes CPU instructions. Just an interesting thing to know about and to be aware about as a computer scientist, as a programmer. So just like to say again, thank you very much, Amicus, and everyone who's here today. You know, thank you for asking your questions, and sorry if I can reply to all of them. And feel free to just ping me later on GitHub or on LinkedIn, or find me on the internet, just so that we can maybe clarify something and share more ideas. So thank you.
Excellent, excellent. Well, like I say, final thanks again, Martin. Obviously, recording's available on YouTube. But yeah, thanks again for joining, everyone. Have a great rest of your evening, or indeed morning. And yeah, hope to speak to you all at some point soon. Perfect.